talk a bit about areas. How do we handle areas below the x-axis? What we said was the integral for something where the function value is positive will give us a positive number. So that's fine. The integral here would be the same as the area. But the other thing we said was if the function value was below, so it was negative, then the integral would give us a negative number. And obviously area can't be negative. So in fact the area would be the negative of the integral if it's below. So that means it's important that we know what a curve looks like. Is it above the x-axis? Is it below the x-axis? Or maybe there's, like this one, there's a bit above and a bit below. If I was simply to integrate from A to C, I'm not going to get the total amount of area because it would end up being area 1 minus area 2 in that integral. And it's not going to give me the right amount. So if it is below the x-axis, how do we handle it? Well, we could simply say it's negative the integral. That would work. Another way, we could simply say, oh, it's the absolute value of it, because that will always give us the positive amount. But the other thing we could do is we could use that idea of swapping the limits around. So if we swap the limits around, it changes the sign of the integral. So we could do that idea as well. A very dodgy cubic. Trust me, it's a cubic. So if we went from -1 to 1, now this is the one that we know it's an odd function, and by symmetry the integral would actually give us 0, and clearly that area is not 0. So we would need to split it. We split it, well, what's below -1 to 0 and what's above 0 to 1? Essentially you're looking at what's the top boundary minus the bottom boundary. And if it's not the same for the whole thing, then you can't just do a complete integral. So in this case, the top boundary is the x-axis, the bottom boundary is the curve itself, whereas on the other side it's the other way around. So I can't do it as a complete integral. Now, when we integrate the x cubed in both of those, of course it gives us the same answer for both of them. But substituting in, we come up with our answer, a half unit squared. Of course, with something like this, I could use the idea of symmetry, because I do know these two areas would be the same. The integrals aren't, but the actual areas are. So another way I could do it is I could have gone, oh well, it would be twice from 0 to 1, same as we would do for an even function. And then that would come up with the correct answer as well. Again, that's the advantage of knowing what the picture looks like. Something like this, however, I mean, it looks like it's got symmetry around -1, but without actually finding those turning points, I don't know for sure whether those two areas are the same. So I can't simply go, well, I'm just going to find twice the area from, say, -2 to -1 or something like that, because I can't be 100% certain those areas are the same. So I need to split it into 2. Now, in something like this is where the idea of swapping the limits around is a good idea, which I've now done. You'll notice in the second one, when I integrate it, I've changed the minus to a plus and swapped the limits around. And the reason why that's nice is to look at both of these things, the top limit is the same. So it just simplifies the calculation out a little bit. I know I'm going to get twice what I get when I substitute in -1, and then minus what I get when I substitute in -2, and also minus what I get when I substitute in 0. Well, what about if we were going to a different axis? The area I'm interested in is actually going to the y-axis instead of the x-axis. We pretty much do it the same way, but now everything's with respect to y instead of with respect to x. That means I need to rearrange my equation, because y equals function x, well, that's with respect to x. I'd rewrite it, I get x equals some function of y. That would be the first thing I have to do. And of course, when I substitute in, now I'd have to substitute in the y values, not the x values. Everything's with respect to y. But other than that, we do it the same way. We just integrate that particular function. So here's an example of that one. If I've got y equals x to the power of 4, but it's actually this area I'm interested in. Rearrange it, I'll make it x equals y to the power of 1/4. I'm going to need to work out the y values. They turn out to be 1 and 16. Then I'll integrate the y to the power of 1/4 rather than the x to the power of 4, and add 1 to the power over the power. Substituting in, we get our answer. But what if I trap an area between two functions? Here's one random function, y equals function x, and there's another one, y equals g of x, and I'm interested in this section that's trapped between the two. Well, we'd have to find the point of intersection, of course. And for this, really, it's just the x values I'm interested in, because that's what I'll substitute in. So I'll find out those, which we can do by solving the two curves simultaneously. We could work out those. But then, if you look at it, all we're really doing is we're going to go, well, what's the area under my red one? What's the area under my blue one? And then the area I want must be the difference between the two. So when I'm creating my integral, I can pull it all into one integral, and whatever that function x minus g of x is, that's what I'm integrating. And of course, that is also the equation I would have used anyway to find the points of intersection, because I would have said function x equals g of x. We'll move it all to one side. It's the same function I'm dealing with. Now let's do this one. X to the power of 5 and y equals x in the positive quadrant. Make sure you read the question, because they're only interested in this section here, not the whole thing, this section here. So top one minus the bottom one. I'll find the point of intersection just in case, we can't look at that and get it, but x to the power of 5 equals x. All right, there's 3 points of intersection. I'm interested in x equals 0 and x equals positive 1. So top one minus the bottom one. Substitute in, we get our answer. So the picture helped me identify which one goes first, which one minus which one. If I didn't draw the picture and I got it the wrong way round, what would happen is I'd get negative a third instead of positive a third. Now if I come up with negative a third for the area, I know I've done something wrong. And that's most likely what I have done wrong. Let's have a look at this HSC question. Now you'll notice the area is below the x-axis. But when you're dealing with something that's between two curves, it doesn't matter. We don't have to worry about above and below. What did they ask us to do? Well, the first thing was a nice little gift question. Find the coordinates of A. All right, let's solve them simultaneously. And we end up with two possibilities, x equals 1, x equals 4. Well, one they've given me already is the x equals 4, so the other one must be the point 1. Substitute in to work out the y value, negative 3. Now go find the area of the shaded region. The top boundary minus the bottom boundary. So x minus 4 minus x squared minus 4x, which is negative x squared plus 5x minus 4. Now we just integrate that. Substitute in, we have our answer. 2005 paper, a little bit more of an interesting shape. So our shaded region bounded by a circle, and we've got a parabola in there as well, but they only want the bit above the x-axis here, that section there. They've told us specifically how they want us to do it. We have to consider the difference of two areas. Now, in this one, if I'm looking at the two areas, why? Because the boundary changes. You see, I'll just draw in a line there at x equals 1. From the left-hand side to 1, it's going to be the circle minus the parabola. But after I go past 1, it's now the circle minus the axis. So there's actually two different areas there. So we would have to break it up. So the area between the circle and the parabola, x-axis. However, I think there's an easier way of doing this. You could look at this a different way. Couldn't I just subtract the area under the parabola from 0 to 1 from a quarter of the circle? Now I've got a nice formula that just works out area of a circle. I don't have to do any integration. Does it satisfy the question? Well, I say I'm still considering two areas. And that's what they asked me to do. It satisfies the requirement. So I'm just going to say it's a quarter of pi r squared minus the integral from 0 to 1. And we come up with, eventually, there it is, pi minus 5/6 units squared. Areas between two curves.